I have a next handout for us. Reckon we'll split it in two. It's the same thing, green handout. I also sent you one by email. We're a few days away from that one at least, but I want to get you plenty of time to get it printed out. There'll be the mass spec handout I'll give you in the lab. This one's on dyings. Resonance, pink sheet. Okay, so, bam. Figure that out. Document M. Okay, at the very bottom. Okay, guys. Resonance. We'll move through here. There's two kind of components to resonance. Understanding the theory, what's really going on. P orbitals there, electrons there. The idea of the hybrid. Okay. Typically, we don't show the hybrid. Even if you're doing a mechanism that involves resonance, you just do the resonance structures. But if we were asked to consider it, then we would understand what the resonance structures are, meaning they're actually, none of them are actually true. They're all sort of fake. Because the true thing is this sort of nebulous hybrid with partial bonds. That's kind of the theory. We also have the, what do you need to do on paper to just do resonance? And that's kind of moving the electrons. And it's got sort of mechanism errors, although we're not doing a mechanism, because when you do resonance, you're not going to a new compound. It's the same exact compound. You don't move any atoms, only electrons. If you ever move an atom, you're not doing resonance. So, in terms of just doing it on your paper, let's just do it here. Here we go. We got a positive charge. How do you stabilize a positive? Move electrons towards it or away from it? Towards it. What electrons can we move towards it? Well, here is the old windshield wiper. Okay, pi electrons, because one of the golden rules. Okay, free information in the back. It's a list of golden rules. One of them is you only move pi electrons. Resonance is about pi electrons. Over there, that's nothing but sigma bonds, and that's sigma electrons. Here, but here's the process on paper. Pi bond, windshield wiper. Just windshield wiper it over. What does that give? Now, this is still here. All right? That gives that. This is a resonance structure, because all this is an alternative way to show the electrons within this given arrangement of atoms. And we just move pi electrons. All right. Now, up here, we only had one resonance structure. Here, we have actually more than one, because now we can windshield wiper this up here. Windshield wiper, it's here. We're just going to move it up there. Now again, when the molecule it does not resonate. It does not go back and forth in real life. This is only us on the board doing it. But what does that arrow mean? By the way, resonance arrow, double-headed resonance arrow, which you always use when you go between resonance structures. What does that arrow give? Nothing here. That's there. We now have pi bond there that windshield wiper up. Okay, let's make it. And plus here, yeah? All right, but we have another. We can take this one and move it here. Everything comes from the arrow movement. We didn't do anything up here, so that should all be the same, right? What did we do? We just moved this over here. So it should just be drawn over there, okay? But look, that's missing a bond now. That's going to be a positive charge. We learned how to do charges during week 1. But you also just anticipate charge there, because this carbon lost a bond. Also, one of the golden rules of resonance is what? Every resonance structure has the same net charge. This compound, this structure here is positive, one positive. So it better be one positive there, one positive here, and one positive here. Can we draw another resonance structure? What if we windshield wiper this down? Now it actually will look a little bit different from the beginning. But people will kind of argue, is this the same or different? It's actually different, but for us we might consider it the same. But what does it give?
Doesn't it give
Here? The positive ends up back on where it began. There is a difference, because here the pi bonds are situated boom, boom, and boom. Now we could come in here and reorganize these electrons and do it more resonance. But reorganizing that to give the one on the end over there doesn't move the charge. And typically when you're asked to draw resonance structures, you're kind of focusing on like maybe delocalizing the charge. There's no other way to delocalize the charge here. Up top, when it was very neutral, I sort of said it's kind of difficult because it's not intuitive what to do. Here, because we have the charge, that's sort of our focus point, and we work to delocalize it. Is this charge just on that carbon? No. It's actually spread over that carbon, and that carbon as well. What does the hybrid look like? What does the true structure of this guy look like? It's a blend of all these. That is, first of all, here and here, everyone's a single bond up there. But what about between here and here? Single. We have some double bond contribution. Actually a lot of double bond contribution. If you consider the one on the end the same as this, okay? So I'll ask this question. How many total resonance structures up here?
4?
In which the charge is delocalized?
3.
4.
4.
Because the first one is considered a resonance structure. Total. Not additional, but total. 4 total resonance structures. I'm not really considered this. This is back to, the charge is back to the same place. It's no longer, it wasn't delocalized. The true structure is a blend of these 4. Okay, let's just forget about that. Or 5 or whatever. Single bond, but it's got double bond character. So what's the bond order of this here, between here and here? Somewhere between 1 and 2. It's 1 there, but it's 2 here. What's the average of 1 and 2? Somewhere in between. Is it exactly in between, or is it more closer to double bond character?
Closer, double closer.
It's actually more closer to double bond character. It's like we're making some ice cream or color. Okay? If white has single bond character, and you have one pint of white, but then red has double bond character, and you have 3 pints of red, then you're going to get hot pink, and it's going to have more double bond character because that's more within. But we don't typically get into exactly where. We just sort of say it's somewhere between 1 and 2. It's 1.5. But it's not exactly 1.5. It's actually, there's actually more contribution of double bond here. Okay. Now if you look at this, it's actually like this all the way around. Example here, is this truly a double bond with a bond order of 2? Or does it have some single bond character? Well, right here shows you there's some single bond character. You assess the hybrid by looking at your individual resonance structures. Single bond character over there. So it's not a double and it's not a single. It's somewhere in between. Bond and a half. Bond, and this is supposed to indicate sort of a half. It's like that all the way around. All these are somewhere between single and double. The bond order is somewhere between single and double. What about charges, though? What's the charge on this carbon? Plus, or is it neutral? Somewhere in between. Let's call it partial plus. What's the charge on this carbon? Does that carbon ever take on any charge at all? Always neutral. So the hybrid should be always neutral. What about this carbon? Got some partial plus character as seen from this resonance structure. You got partial plus there. Where else in the ring? There and there.
I can't draw that thing. Partial. Let's make it a S.
This is the true structure of this cation. The charge is not sitting right on this carbon. It's delocalized onto several carbons. That's a stabilizing effect. If you could see the electrons, you would not just have pi electrons here. There's also some pi electrons through here. Some additional pi bonding through here. The hybrid gets a little complicated. One reason here, it's not a perfect blend. Up here it was a perfect blend, right? Because we drew this resonance structure, and the hybrid is what? Exactly 1.5 here and here. Because it's an exact of a single and a double. What's the perfect average of a single and a double? 1.5. Okay? That's supposed to be the same length. Your bond order is the same as bond length. Here you go. Which bond is longer? AB or BC?
AB.
Which bond is longer? Which carbon-carbon bond is longer?
AB.
Trick question. They're the same. Those two bond lengths are the same. Because we know that that's not the true structure. The true structure is this, right? The charge, what do we got? Partial plus, partial plus. Here's your true structure. The bond order and thus bond lengths of the two carbon-carbon is the same. We've got to know that when you see such. Okay.
Can you roughly estimate by the number of resonance structure how it'll, like, are those bonds, because there's 4 resonance structures, going to be closer to 1.25 or no?
We just don't typically get that precision. We just say it's something 1.5, where really we understand it might be closer to 2.
Right. Okay.
That's as far as we kind of take it. Now, if you get into some calculations and stuff, yeah, but for us, what I just told you is that's it. Unless we see examples where it's going to be a perfect blend. Okay, here we'll talk about this. Which is the major resonance structure? That is, of the fake ones we drew, which one is closest to what we expected? This could be a little tough in this case, but we'll ask that more and more. The answer here is the original one. Because the reason is the benzene ring is maintained. Very magical. Okay? But this would be major. These would be called minor resonance structures, or minor contributors, because they contribute a little bit less to this. But although they contribute less, there's 3 of them, so it's sort of... okay, this cation, we're able to do this resonance because we're right next to this benzene ring. This is called a benzylic cation. Because the carbon adjacent to the aromatic ring is called a benzylic carbon. The benzylic cation is very stable because it's resonance delocalized. we'll see these a lot. This up here, by the way, is called an allylic cation. When it's next to just an alkene. That term is less common. Much more common to talk about benzylic cations. But this is probably in your textbook. It's just not referred to as much. Okay, we'll see these things as we go along. Let's look on the next page. Okay, in the previous section, we stabilized a cation with a pi bond. That was the heading. That's what we did there. Next, we're going to stabilize with a lone pair. Oh, by the way, we did sort of the nuts and bolts working. How about some theory here? How many p orbitals in the benzylic cation here? This one shown. How many p orbitals were here? 7, right? How many pi electrons in the system? 6, right? Okay, that's some of your theory. I see it? Seems like the pink is not showing up as well. Is that right? You're able to see everything? Okay. We got this cation here, this carbocation. How can we stabilize it? Well, here we have a lone pair. What we can do is these electrons can just move in, fall in. What does that arrow mean to you?
A bond.
It's moving in. We did that on day 1 when we were doing resonance Lewis structure. Actually, when we did that, we were doing resonance. Just didn't call it resonance on that day 1. We said something like, this guy needs a bond, and we're going to ask this over here to share. Okay? Well, that's resonance then. What does that give? We now have a double bond here. How many lone pairs left on oxygen? 1. What's the charge now? What's positive?
Oxygen.
Oxygen is positive. That's not a typical oxygen. We learned on day 1 what a typical oxygen should look like. And if it ain't typical, it's kind of like, hey, I'm probably charged. Does that arrow make sense to give that structure? I'm tempted to call this a mechanism arrow, but we're not doing a mechanism here because mechanism sort of implies we're going to another compound. But it's the same as a mechanism arrow. Right? There you go. Can you do any other resonance structure?
Double bond on the other side?
On the where?
Other side of the oxygen?
What do you mean? How?
I don't know.
What would your structure look like? Do it using your arrow movement on your paper.
That wouldn't.
Yeah, you couldn't just like flip that over, could you?
Well, it's a common thing I want to address. You guys tend to want to, I know you're just throwing out comments, that's great, but ultimately the answer is, well then, do it on your paper and assess what you're considering. Then, you're going to have a very tough time using arrows to draw a next structure. And at that point, it should clue you in that it ain't possible. Yeah. There's no pi electrons over here, first off. This is a carbon with 3 sigma bonds to H. There's no p orbital there. Anytime we're doing resonance, it really starts from just all p orbitals lined up. And you have a system. And if it's not in that system, then you ain't doing resonance with that system. Here's our on the board there. That's the only resonance structure. But what did we do? We did what the title says we're going to do. Is the charge delocalized? Yes, it's moved from carbon to oxygen by doing resonance. Okay? Which structure is the better one? That is, which one is major?
The left one,
The
the
second,
Which one do you like better?
first one.
the one on the right.
That oxygen doesn't like to be positive.
I agree, oxygen doesn't like to be positive compared to carbon. But still, this one's major.
Ah.
This is minor. That is, they're not equal contributors. One's better. Why is this better? Yes, it's bad that it has oxygen as positive, but it's got more bonds.
Entropy is.
Because we just made another bond when we went over there. And that's the key thing there. What's another reason? All atoms have octet. Which sort of just is almost a restatement of the first. It's a consequence or a result of the number one. But see, over here, the carbon does not have an octet. Here, and this is why oxygen is okay with being positive, it still has an octet, doesn't it? 2, 4, 6, 8. If it has an octet, these electronegative atoms don't mind being positive. I'm sure this is discussed on the golden rule page. But you never want to leave something that's more electronegative without an octet. The atom will be very mad and it will hunt you down and make you pay for it. But this oxygen has an octet. Major. That is, what does a hybrid look like? Well, we could draw it. But is the hybrid going to look more like this one or the one on the right?
On the right.
That's what major means. The hybrid's going to look more like that. So is there more single bond character between the C and the O or more double bond character?
Double.
There's more double bond character. But it's not full double bond because there's also some single bond character. Okay, let's do the hybrid. What do we have? Okay, oxygen. What's the bond order between the O and the carbon? Approximate. Somewhere between 1 and 2. So let's make it sort of somewhere in between there. Again, we're not, okay. What's the charge here on this carbon in the hybrid?
Partial positive.
Partial plus, partial plus. Now there's a lone pair there as well. But that's the true structure. The true structure has, this lone pair is sort of semi-bonding in here. That makes sense because the iron electron is going to be attracted to a positive. All right? Your carbocation, I've got a lone pair. We've done this before. What's the lone pair going to do? It's going to be sort of attracted. Okay? But hold on. I don't want to be too attracted because I don't like becoming positive. So I don't want to become a full double bond. So let's just make a pinky bond and a bond and a half. The oxygen's like, I'm a little bit greedy. I don't want to give you all my electron density. Right? And that's how it is. Pinky bond. Okay. Next one. Show all possible resonance structures in which the charge is delocalized. Show them. There are two additional ones here. Both, two different types. We've looked at both types. Well, I see this lone pair here. Oh, I know what I want to do up there. We'll do this. Then we'll go back and let's do a little theory up there and let's maybe draw some orbitals in. Okay. I can do this, yeah. Classical on the board mechanism, resonance. What does that give? Positive on nitrogen, because all resonance structures have the same net charge. It all comes from your arrow movement. Let that be your guide. That's it. And I'm going to call that arrow A. What else could we have done here?
The windshield wiper.
We could do the other way, and we could windshield wiper this over and call that B, and that would give boom, boom, boom. Nothing there, but we windshield wipered over, and that's positive there. So I'm doing theory up there. Let's just do theory down here. Let's look at the p orbitals here. Okay. The true structures are blended these. Okay. Is the charge delocalized? Yes. The charge exists on nitrogen, that carbon, and that carbon, partial plus in the hybrid. Which one looks major?
Far right.
Yes, that one's major. Oxygen has not kept. Which one's worse? That's kind of a bad question, but maybe for us it might be all right. Which one looks worse? I don't like the question, but what type of cation, carbo cation is this? Primary. And primary is a pretty lousy cation. But see, this is also strictly primary, because it's only bonded to one carbon, and it's not a clear answer which is worse. It's a clear answer which is best, though. Okay? All right. Let's go back to August and September. What type of orbital is this lone pair in? What type of orbital is that lone pair in? We spent a good amount of time on that for a reason, because of today. And what type? Okay. Lone pair in a what? P orbital. You all knew that. You're just unwilling to say it, right?
Yeah.
By the way, next Friday we have the speaker on campus, 1 o'clock. Okay. I sent out an essay that he took time to write
17.
earlier. Yeah, I think this one has 2 B's. Essay BB.
Oh,
Or
okay.
there's one of them's only 1 B, one has 2 B's. I realized that at one point. I'll probably send out his essay again. We can talk more about that. That's next Friday at 1 o'clock. Be in the room next door. Question?
That last one, what would you say the reasoning is that one's the major structure?
Same as above. Okay. Anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital. Sound familiar? Okay. By the way, if this lone pair ain't in a p orbital, you shouldn't be doing resonance with it. Because resonance only involves electrons in p orbitals. Right? If we drew the p orbitals, first of all, any one of these, because the orbitals are always the same. I mean, let's draw to this one. I'll do it over here. I've got, what's the hybridization of the carbocation? First off, lone pairs in the p orbital, right? This is going to look pretty when it's done. All right. There's lone pair. What's the hybridization of the carbocation? sp2 with an empty p orbital. Sure, we did plenty of that in before. Got a p orbital, but it's empty. All right. What is a pi bond? How do you make a pi bond? P orbital, right? I mean, that's the pi bond that's shown there. How many electrons in each p orbital? 1, 1. Overlap makes pi bond. This one's empty. How many p orbitals total in the pi system? 4. You see, we're doing resonance all across the molecule. There's no carbon or anything without a p orbital. All atoms have a p orbital. How many electrons in the pi system? 1, 2, 3, 4. That's empty. 4. right? There it is. All these orbitals are interacting. And that's what resonance is. But here's the thing. Once they interact, it becomes one system with 4 electrons. And now, the electrons are no longer sitting where you think they are. They're all in there. But are they equally in there, or are they more sort of towards a certain way? Or is these all equal, or is one more favored? More favored. That means the electrons, well, if this is favored, it almost looks like it's 1, 1, 1, 1, right? Pi bond, pi bond. But that just gets where it is. You have one conjugated system. The electrons are just all in there. We can think that maybe they're more towards one way. I can also use this analogy. If I brought in a garden hose, it's 8 feet long or whatever, filled it up with water, is the water going to spread out all in that garden hose? Yeah. Or is it just going to stay on the end? No, it's going to spread out in the whole hose, I think, right? Can I make it go to one end? What if I raise the hose up over here? Will the water go to the other end? That's akin to maybe having an electronegative atom on that end. Because if you have a hose with a greedy oxygen, it's going to pull the water towards it. That's some of your theory. In the end, that lone pair is going to be It has to be if we're going to do resonance with it. And we tried to get it that 2 months ago. Month and a half. Okay, we'll continue to build. Let's see. Examples of resonance affecting regiochemistry. Speaker next week. We might have probably another visitor next week. You have an Alicia Keys? Yeah. Yeah? Yeah. She may visit next week.
What? Someone else named Alicia Keys? Huh?
Our resonance effects. What's going to be the product of this reaction? This is a good old alkene hydrobromination. What's going to be the regiochemistry?
Right.
The right one?
The question is really, where's the cation going to form, right? Top or bottom? Do this on your own. Consider both cations and which cation is most stable. Over here, which regio product? The answer is really where's the cation, left or right? Consider the 2 different cations, which would be most stable. Because the more stable cation is what's going to form, and then that's going to give you the product. Because if cation is there, then iodine will add there. So this is sort of using resonance to predict regiochemistry. Please try those. Let's move to anions. How do you stabilize an anion? Do we want to move electrons towards it? No, that doesn't sound intuitive, correct? We've got to move electrons away from that side. We want to go towards neutral. How do we do this? I call this the old in and out method. We're going to take these electrons and move them in here to make pi bond. But guess what? This carbon can't make another bond. You can't have 5 bonds to that carbon. So you got to also move those out. What does this arrow movement do? Pi bond there. What's now on this carbon? Lone pair. And that's a minus charge. So that's the old in-out method. Now, you ain't going to find that in the textbook. You ain't going to call it the in-out or windshield wiper. Those are my terms.
How's that different than the first example of the
But before we
resonance?
had cations.
So
We
just
were
the
moving
difference-
electrons towards the cation.
Okay.
Here, The carbon has electrons. We want to move electrons away from this carbon. That's what we're doing. Because now the charge has been delocalized onto another atom. Delocalization of charge is a common thing that comes from resonance. Okay, which one's major?
It's like a sensitive.
These are equal contributors. You see, they should be equal. They're the same, essentially. What's the hybrid look like? What's the BO between these two kernels?
1.5.
Perfect blend between double and single, 1.5. How about over here? Same thing. What's the charge on the N carbon? Partial minus. Partial minus. If we could see this anion, this carbanion, it would look like that on the right. The charge is not just on that carbon, it's delocalized onto the other one. Here the BO is exactly 1.5 because it's a perfect blend. Consistent, right? I mean, it's a very similar discussion, yeah? What about down here? Do resonance on your own. As many resonance structures as you can to delocalize the charge. We'll look back at that. Let's go back to neutral molecules. We actually started with neutral. But these neutrals are going to be a little bit more intuitive because they're going to have like a lone pair and a heteroatom, etc. Underline this comment. When you have lone pairs, it's potentially the first place you want to kind of start with your resonance. If the lone pair is in a p orbital, because if the lone pair is in a p orbital, ignore them. You can't do resonance with them. Is this lone pair in a p orbital? Yes, anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital. So that's what a p orbital. Once recognizing that, that's where you want to start. And what we can do here is, even though it's not charged, we can still make use of this lone pair and do our resonance. These electrons can move here, and these can be pushed out, the old in out. What does that give? By the way, anybody know the name of this compound? Or class of compounds if it had substituents on it?
Isn't it
Aniline, or I just say aniline. Okay? Or we could have substituents and it would be called an aniline, like a phenol. This is an aniline, okay? This it? Anything missing? Charges, that's positive. What should be the net charge of that resonance structure? Should be net neutral. This is neutral. What am I missing here? Missing an anion here. And the charge is net neutral, as it should be. Can we keep going? Lone pair, continue to go with the lone pair. Where can it go now? On the board, not in real life. It's always just there in real life. But on the board, we can now move it in here and move. This is a pi bond. You can either call that the pi bond or this one. I'm going to just do it like this. Move the pi bond onto this carbon. What does that give? That now have pi bond here. Nothing there. This is ugly, right? And then what's here? Lone pair, and that's a minus. Now we can have these electrons come here, and these come here. Resonance arrow, Charge. What would be next? We can move these where? Here?
Those back out.
And importantly, if we move these here, what do we got to move out? Can I break that away? No, that's a sigma bond. Never move any sigma bonds. The pi bond, it looks like a pi bond, it is. We move the pi electrons back here, but what does that give? Well, it's essentially the first, if you don't argue that the pi bonds in the benzene ring have been delocalized or shown resonance. And I'm not going to include that, but yeah, someone can say, well, what about the resonance structure just here? Okay. Please read your description of what we're doing. Which carbons of the benzene ring of aniline are most electron rich? Electron rich, highest electron density. If you were showed this compound and asked which carbons of the ring are most electron rich, which ones would you say are? I would look at the resonance structure. This lone pair is going to donate in here. And which ones are electron rich? That one, that one, and that one. Those are the most electron rich. So that's where the minus falls. Okay? We got to please be looking ahead here. We're going to have to move ahead. Please be doing problems, whatever is there. Okay, if it asks you, it looks like you need to draw resonance structures, then please do them. We'll see how we did on Monday. See some of you this afternoon. Mass spec, I will give you that handout in lab. Please have a nice weekend, guys.